Today we're going to look at SO2, which is sulfur dioxide. So first we have one sulfur atom, which has 6 valence electrons because it's in group 16 of the periodic table. Then we have 2 oxygen atoms. Oxygen is also in group 16 of the periodic table. And there are 2 of them. 2 times 6, 12 valence electrons. So in total, 18 total valence electrons. For the least electronegative atom, which is the element on the periodic table which is farthest from the top right, we find that it's sulfur, so we write that in the middle of the Lewis structure. And then we're going to put oxygen on the sides, just with single bonds. And then we're going to see, we took out 4, so 18 minus 4, we have 14 valence electrons to put around. So let's just start distributing them. Let's do 2 here, these electron pairs. Let's see if this works. This fulfills the octet rule, but the formal charges are not minimized because this only has 5, 1, 2, 3, 4, 5 electrons going into it, sticks and dots, and oxygen has 7 going into it, and both of these need to be at 6 to minimize formal charges. And we know that sulfur can have an expanded valence shell, so we can just draw this other stick, and you can see that we've used 8, 8, and 2, so we're at 18 total valence electrons, which matches what we should be. And looking at this, we see this is what it would look like for a shape, and with the electron pair, for the electron pair geometry, it would be trigonal planar. They're all in the same plane with 120-degree bond angles because 360 divided by 3 electron groups. But for the actual shape, not the electron pair geometry, which is only considering the bonds, it'll be bent. And then if we look at the sketch, it's actually just going to be this, because it's all on one plane. You could also just draw these as 2 flat line bonds. And so we know that it's polar because it's trigonal planar and these 2 dipole moments will not cancel out. And so that means it's going to have dipole-dipole interactions as an IMF and also dispersion, just like any other molecule.